So I'm going to tell you about some work done in Julie Grolier's group. The bold names are the ones who actually did most of the work, and the not so bold names are the ones who usually get to give the talks about it. And so, like I said, this is going to have a lot of overlap with the previous talk. The difference is where I'm going to talk about doing it with a Spintronic oscillator as opposed to the optical systems. I want to start off by giving a little bit of personal opinion on where I see the field, and so we can fight about this afterwards if you disagree. So when we think about brain-inspired computing, it spans a whole range of things. The two old parts of the field are at the top, the neural networks, which started a long time ago. And these are actually in heavy commercial use already. Everybody with their smartphone has something that's making use of these neural networks. On the other extreme, hardcore neuromorphic computing was a field that originated where people were trying to make hardware models of the brain to understand the brain. And the part of the field that I'm interested in is actually trying to see if we can copy some of how the brain computes to do things like what the neural networks are doing, but do it in a much more energy efficient way. And one of the things that the brain does is it operates in a dynamical regime as opposed to a quasi-static regime like you have with the neural networks. And the hope is that we can figure out a way to do that more efficiently and hence contribute to the computing field. Now, what I should say, and we all need to keep in mind, because this is kind of what we're all doing, I mean, the train has left the station, right? We're competing against CMOS. They already have these big chips that have lots of neurons and lots of synapses on them. They're well controlled, they're manufacturable. And so what we have to do isn't competing with CMOS, but we have to compete with what CMOS will be when we get something that's at an implementable stage. And they're moving really fast. There's lots of resources that are going into making these chips. So there are some things that CMOS does really well for neuromorphic computing. One thing is, if you think about the way the brain works, is that the incoming spikes don't provide the energy for the outgoing spikes. There's a local energy source that gets tapped into chemicals in the brain that provide the energy for the outgoing spikes. That's a natural thing in CMOS, and it's not a natural thing in a lot of the physical or Spintronic type devices that we think about. And so that's a really crucial feature to think about how you're going to get the energy to provide the fan out, because the brain has really large connectivity, and I suspect that plays a crucial role in the power of the brain. Speaking of the connectivity, that's also something that's hard to do if we're stuck working in 2 dimensions or quasi-2 dimensions. It's hard to think of how we're going to attach 10,000 wires to a particular neuron to feed those off to other neurons. A way that that's done in CMOS is to actually do multiplexing in the sense that they're not using a true analog spike. They're doing a digital representation of an analog spike, which can then share a common bus to get large point-to-point connectivity. And so that's another thing that CMOS does really well. However, these chips still don't have the type of energy efficiency that we hope to be able to eventually someday get. And so my opinion is the way to go forward is to figure out how to make CMOS do its job better by novel devices. I think if we try to aim for an independent architecture that's going to replace CMOS, the chances of us getting something that's as cheap to make as CMOS is pretty close to zero. However, if you can come up with something that will really make their systems better and make a convincing case of it, they'll incorporate that. So, for example, magnetic tunnel junctions are now being built into the tools that are going into the most modern fab plants. And so if you have an architecture that uses magnetic tunnel junctions, Those are manufacturable at this point. And so the barrier to entry for effects based on those are much smaller than they are for other things because the tools already exist. The nice thing about magnetic tunnel junctions is you can do lots of different things with them. You can make non-volatile memory out of them. And that's likely to be the first implementation that you get for spintronic devices in neuromorphic computing is the type of things that Fukuyama talked about the other day, where you're doing an associative, I'm sorry, I got the wrong speaker. Monday or Tuesday, one of the talks was about making an associative memory using embedded magnetic tunnel junctions for memory. That type of thing is real simple to do. Local storage of information, so you're breaking the von Neumann bottleneck. That's, I think, very likely to happen. But there's other things that you can do with magnetic tunnel junctions. If you make them bad or smaller, they become super paramagnetic. That can generate stochastic processes. And there are a number of different ideas that people are pursuing where that might have some advantages. And some of the later talks in this meeting will talk about some of those. The other thing that you can do is you can make oscillators out of them where you drive them with a DC current or voltage and you get an AC signal out. And because you have oscillatory processes going on in the brain, you may be able to take advantage of the oscillator aspect of the magnetic tunnel junctions to do something novel that it can only be done much less efficiently in pure CMOS. All right, so what I want to tell you about today is something you learned about in the previous talk, which is time-multiplexed reservoir computing. And based on the idea that people always get much less out of the talk than you think they do, I will repeat the basic ingredients of that, and feel free to nod off if you got that completely in the last talk. And then I'll talk about applying it to a couple of different problems to illustrate some of the aspects that are important for making it work. A simple problem of separating sine waves from square waves, then spoken digit recognition, which is a more realistic or interesting problem, and then I'll come back to the sine square definition and the two different things there. We're going to take advantage of different aspects of memory to try to understand what type of role each play. So here's the standard diagram we always start off with, a feed-forward network where the information flows from your left to your right, and it's a quasi-static system. The state is determined by the input in the first layer, and then that determines the second layer, third layer, and you don't have to worry about any sort of dynamics. If you now make some connections that aren't just forward, but also backwards, like it was described in the previous talk, you develop loops, which means that this now has intrinsic timescales, and the state of the system doesn't just depend on the inputs, but it depends on the previous inputs and the inputs before that. And so with this time dependence, it becomes natural to do things like predict time series as opposed to images, again, as was said earlier. The problem is training these kinds of systems is rather difficult, because if you really wanted to train it, you'd have to take the state of the system at all times and adjust the weights based on that full time dependence. And that gets really difficult. And so the approach people took to reservoir computing is to say, okay, I'm not going to adjust the output weights. I'm going to take random weights for the input, and then I'm just going to do a simple linear fitting of the output weights to try to get the answer that I want. And that's really simple to do. As described earlier, you just take all the outputs, make a big matrix, invert it, and you have your weights. You could also do simpler training protocols, but that's for demonstration purposes. That's the simplest one. And so then if you have this reservoir, you could imagine, okay, let's make a simple ring type geometry where I have nodes distributed in a ring. And then as done in the previous thing, all right, I'm going to make those all virtual nodes, and I'm going to do that by time multiplexing. And the way I'm going to do that is I'm going to discretize the input series, and then I have to, at each particular point, I have to give that information to each of the nodes. And the way I do that is multiplying that input value by a time-dependent weight matrix. And so when I do that, here I have a moderate signal, so I have a moderate copy of the weight matrix. Here it's low, I have a small version of it, and then I have a bigger version back when the signal's bigger. And so this corresponds to the ring, giving the input into each of the nodes. And then what I'm ultimately going to put in is this particular waveform. And then I'm going to capture the waveform and look at its average value over each one of these nodes in each of those different time steps, and then use that to analyze the information that was put in. Is that crystal clear? If not, please ask. You've had it twice.
What defines a good mask?
In our case, trial and error. It turns out it's not something that changes too fast, right? You know, if you had one, it seemed that the masks that worked well had long stretches of uniform behavior, but also some shorter behavior. I don't have a good theory for that.
It must change much faster than the input time series, because you want to have many.
Well, so I mean, this is the input time. This is a discretization of the input time series, and then this is imprinted on that. So yes, if I am discretizing this faster than it is, it doesn't make any sense. So yes, I'll show that in a little bit more detail a little later. All right. So here's how Julie and her students and postdocs implemented this. It's just a simple single magnetic tunnel junction that's functioning as a spin-torque vortex oscillator. So you feed a DC current through it, and it oscillates with a particular amplitude. And then we're going to pass in that waveform that I described earlier, capture the amplitude of the AC signal out, and use that to analyze the problem. So if, for example, if I sent in an input that looked like this is the response that you see. And so it's gray in here because that's actually individual lines of what the actual time trace is. So it's oscillating much faster than the amplitude is varying. And in the future, one would hope to take advantage of these oscillations, using them to communicate with other oscillators and make a richer system. But for this, we're just going to take advantage of the amplitude of the signal here and look at the amplitude of the AC response. And you can see that because of the magnetic damping in the system, it doesn't respond instantaneously to the input. And that's what's going to provide the memory in this system to start off with, is this decay of the amplitude of the signal as a function of time because of the finite magnetic damping in the system. The other thing that you get is if you look at the amplitude of these oscillations as a function of the DC input, you get this nonlinear output. And that nonlinearity is going to play a crucial role in having this be a useful system. All right, on to sine square identification. All right, so this is the basic problem we want to solve here. Is I have waveforms that randomly go from a sine type shape to a square wave type shape. And you can see we've done a rather crude discretization of these two things. But the thing that makes it an interesting problem is that at least over a short time scale, this input is identical to these inputs. And so we're going to have to figure out a way to be able to distinguish that point from these points. And so here's an example of the input waveform, and then at each of these points, we're going to multiply it by a mask that looks something like this, so that this is now spread out over here, and you can see all the different virtual nodes in the system. And this is how the oscillator amplitude responds to that masked input. And you can see what we've chosen is that the decay time is several node spacings. It's not spread out over the entire system. It's not shorter than the node-node coupling, but it's on the order of a few. And that's where you seem to get the best performance in these types of networks. So here is an input. Here's what the output looks like. And to do the job, we have to be able to look at this waveform and this waveform and have a statistically significant enough difference between them that we can construct output weights such that they will say that that's a sine wave and that's a square wave. And that's what we show here. Here are the two identical inputs on your left, and on your right, the difference in the output. And this is either very similar or very different depending on what your noise level is. And here it's the noise level is low enough that those are very different, and that will enable us to distinguish those two, whether they are part of a sine wave or part of a square wave. And so what we're going to do is take these output traces and then use the values of the output trace at each of these virtual nodes to multiply by the weights, such that for all of these waveforms, we're going to get a value of 0, but for all of these waveforms, we're going to get a value of 1. And that's then going to allow us to interpret whether we have sines or sine or square waves. And that's what's illustrated here for a long trace. So the system is fairly noisy, as you can see. If you think about the fact that those two waveforms were rather similar, that means that the weight matrix is going to have to be somewhat singular. And that's going to tend to amplify the noise in the system. And so you can see that error in the noise here, that where you nominally want it to be 1, sometimes it's 0.7 and sometimes it's 1.3. But if you're able to say, all right, I want to everything below 0.5 is a square wave and everything above 0.5 is a sine wave, I can get perfect recognition of the sines and squares doing it this way. All right, now I want to switch on to maybe a more interesting task, which is trying to identify spoken digits. And so the database that we're going to work with is 10 speakers speaking 10 digits 10 times. So I have 1,000 elements in the database. And I'm going to use some of those as a training set, and then some of those as a validation set, and see how well we can train the system to recognize those spoken digits. All right, so here's the way it would work. We start off with the audio form on your left. We do a spectrogram analysis, and this is to say, okay, I'm going to take some of the frequency components in each time window and track those frequency components as a function of time. So it's sort of a mixed frequency time representation. Then I'm going to multiply that by this input weight matrix, which is going to give me the preprocessed output here. Then I'm going to send that through the oscillator, record the trace, train it, detect the output. And when we do that, we discover that we can get 80% recognition of the spoken digits. And what's being varied here is the fraction of the utterances that we're using for training and the fraction that we're using for validation. So if we do more training, we get better results. So that's not so surprising. But the real test is, okay, we've done all this pre-processing. Does it work if I just take the preprocessed input and analyze that without passing it through this oscillator at all? And when you do that, you discover that you're down to 10% recognition, i.e. it's completely random, nothing happens. And so the oscillator here is playing a really crucial role in whether you can recognize spoken digits. But this isn't particularly good performance relative to the state of the art. And the reason for that is this analysis here where we use the spectrogram, if you go and use a cochlear preprocessing, which models the way the ear performs, but which is like a spectrogram, but it has nonlinearity built into it. And so when you do that, you discover that you can get much better, but that you can also get much better if you just take the oscillator out. And so the nonlinearity that's being done by this cochlear transform provides a lot of the recognition that you're ultimately able to do, and the oscillator adds a little bit more to it. But if you start in with cruder data, which is less linearly separable, then the oscillator makes a very big contribution. And this 99.6% spoken digit recognition that you get is comparable to what people get with any particular type of approach they're doing. And so the interesting thing here is that you're able to do this, if we ignore all the pre-processing and the post-processing, with just a single nanoscale spin torque oscillator. So here is some idea of trying to understand what's important about the oscillator to get good performance out. And so here is a map as a function of the applied magnetic field and the DC zero offset current on how well you do. And this is on the on the sine square performance, where we're looking at not the recognition, but the noise level that you're getting in those signals, which tells you how well you can do on the recognition. And you can see that you get quite low performance, which is good, at some points, and then poor performance at other points. And the question is, why is that? And so by playing around with various things, what they discovered was that what you need is a large nonlinear output compared to the intrinsic noise on the system. Not so surprisingly. So the noise is measured, if I just set it at this particular DC bias I put in there, how noisy is the signal? That's this delta V. And then you get when I put on a negative current, how low does it swing? If I put on a positive current, how high does it swing? You want to maximize that as much as possible. And that happens to cover the most nonlinear regime of the oscillator output. And so when you make this ratio, you see that that does a very good job predicting where the oscillator is going to have its best performance. All right, now I want to switch back to the sine squared definition, but I'm going to change the regime we're operating in. And something got lost there. So there's supposed to be axes on this plot. This is time. This is the signal that's being provided. And what you're seeing is that the intrinsic memory decays in this window here. And now I've added this feedback loop such that every time tau, the output of the device gets re-injected back in. And so then there's an echo peak here and another echo peak at each of these, and these decay off. And what we're going to do here is operate in a regime where this time scale is much faster than the small separations between the virtual nodes. So the intrinsic memory is not going to play a role here. And all of the memory is going to be provided by this feedback memory. And that gives us a geometry that looks something like this. It's kind of peculiar. Now, because there's no intrinsic memory, there's no connection between any of the nodes like this. But with the feedback coming in after a time tau, there's feedback of each node to itself. And so the network consists of sending in some weighted input to each of these virtual nodes and collecting their behavior, but they're essentially only coupled to themselves. And then I'm going to start off with the discretized signal, multiply it by the mask, capture the output of the device, combine that signal, and compute what the output is supposed to be. And so here what the trick is, this is another way of showing what I showed you earlier. I've color-coded well, when I say me, I don't really mean me. I mean we, as opposed to student who worked really hard on making these plots. So I should give them credit for it. I've highlighted here the 5 signals that are nominally the same without some type of memory in the system. And here is the output for each of those, including a band indicating its standard deviation. And so what you can see is there's no statistically significant difference between this curve and these curves. And so when I try to do the sine square recognition, I get a rather large error rate because these ones are completely mushed up. And sometimes I get a sine for these, and sometimes I get a square for these. But when I put the memory in, the responses all change. And now if you look, this orange curve here is statistically separate from all of the other curves there and also here. And that gives me enough separation that I'm able to get a rather good recognition rate in this type of output. And so here, again, the memory being provided by the feedback is playing the crucial role in whether we're able to distinguish these nominally identical, except for context, inputs. All right, so that's what I wanted to tell you today. Basically started off with the assertion that what I think we really want to aim for is figuring out what we can do to make CMOS better, because they're going to be getting better on their own, and they're going to be doing it faster with more resources than we are. And it's going to be hard to compete with their manufacturing base. And so what we really want to be able to do is to help them rather than try to compete with them. Looking at magnetic tunnel junctions has the advantages that that's already built into the system that they have. And so I encourage people to think about that, because that's maybe the best way in which Spintronics is going to be able to make a contribution to neuromorphic computing. Told you about time multiplexed reservoir computing, where the memory and the nonlinearity played crucial roles in different types of tests that were done to try to evaluate that. But now the question is, okay, where do we want to go with that? It's probably true that a single oscillator reservoir isn't going to be playing a role in real implementations of reservoir computing. One thing that might be useful, however, is if you had a network of spin-torque oscillators where they were coupled and they had much richer behavior, so that you wouldn't need to do this high level of pre-processing to pass a signal into that. And the other thing that's missing from this, I showed you all these great CMOS chips at the beginning, but even with those, people haven't really figured out how to use them to really make a killer solution to a problem. And we have that same problem here. We're missing the algorithms that will tell us how to make our devices useful. And so there needs to be an integrated thought process on what are the advantages that these devices might have to offer, what algorithms can take advantage of those, or if we have this great algorithm that needs these particular devices, how can we get those properties? And these really have to be talking to each other to make a lot of progress. Thank you for your attention.